An amazing science.
Observe the given scenario. What happened to the speed after the moving astronaut collided with the one at rest? Yes, you're right. It decreased. Why did the speed decrease? Correct. Their masses added when they stick together. Suppose that each of them weighs 50 kilograms and the speed of the moving astronaut before collision was 10 meters per second, which then became 5 meters per second when they moved together after collision. How will you compare the momentum before and after collision? Correct. They are equal. With the same amount of momentum, when the mass increases, the speed decreases. Situation similar to that example was the basis of the French scientist and philosopher Descartes to come up an idea about momentum. Descartes introduced momentum before Newton and concluded that the total amount of motion is the same before and after collision, as observed in the two astronauts that moved together, ending up with twice the mass moving at half of the initial speed. Descartes invented the concept of momentum, meaning amount of motion. So, according to him, for a moving body, the momentum was just the product of the mass of the body and its speed. Let's analyze the example. Initially, only one of the astronauts had momentum, an amount of 50 times 10 equals 500 kilogram meters per second, since its mass is 50 kilograms and its speed is 10 meters per second. After the collision, there is a total mass of 100 kilograms moving at a speed of 5 meters per second. So the final momentum is 100 times 5 equals 500 kilogram meter per second. So the total amount is equal to the total initial amount. It is then obvious that in the given scenario of the two astronauts moving together, total momentum is the same before and after the collision. There is, however, a problem here. Obviously, one can imagine collisions in which the total amount of motion is defined by Descartes as the product of mass and speed is definitely not the same before and after. Say, for example, two people on roller skates of equal weight coming directly towards each other at equal speeds, but opposite directions. And when they meet, they put their hands together and come to a complete stop. Will the momentum stay the same after they meet? Definitely not. Clearly, in this situation, there was a plenty of motion before the collision and none afterwards. So, the total amount of motion definitely doesn't stay the same. In physics language, it is not conserved. Descartes was hung up on this problem a long time, but was rescued by a Dutchman, Christian Huygens, who pointed out that the problem could be solved in a consistent fashion if one did not insist that the quantity of motion be positive. So in other words, if something moving to the right was taken to have a positive momentum, then one should consider something moving to the left to have a negative momentum. With this convention, two people of equal mass coming together from opposite directions at the same speed would have total momentum 0. So, if they came to a complete stop after meeting, the total momentum before the collision would be the same as the total momentum after, that is 0. And momentum will be conserved. In the description and example, we are restricting ourselves to motions along a straight line. It should be apparent that to get a definition of momentum that is conserved in collisions, Huygens really did was to tell Descartes that he should replace speed by velocity in his definition of momentum. It is natural extension of this notion to think of momentum as defined by momentum is equal to mass times velocity. It turns out experimentally that in any collision between two objects where there is no interaction with third objects such as surfaces, interferes, the total momentum before the collision is the same as the total momentum after the collision. Descartes introduced the concept of momentum and the general principle of conservation of momentum in collisions before Newton's time. However, it turns out that the conservation of momentum can be deduced from Newton's laws. Newton's laws, in principle, fully describe all collision-type phenomena and therefore must contain momentum conservation. The law of conservation of momentum states that in an isolated system, the vector sum of the momenta before and after collision are equal. When we say isolated system, it is a system where there are no external forces present and no loss of mass between objects. So, in equation, total initial momentum is equal to total final momentum. In symbols, Pi total equals Pf total. Specifying further the equation, m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, where m1 is the mass of the first object, v1 is the velocity of the first object before collision, v1 prime is the velocity of the first object after collision, m2 is the mass of the second object, v2 is the velocity of the second object before collision, and v2 prime is the velocity of the second object after collision. Conservation of momentum can be observed in collisions between objects. Collisions fall into two main categories: the elastic collision and the inelastic collision, in which inelastic collisions can undergo further into perfectly inelastic collision. Let us now compare the three types of collisions mentioned. Momentum is conserved in all types of these collisions. However, kinetic energy is only conserved in elastic collisions. Objects separate after collision in inelastic and elastic collisions, and deformations only happen in inelastic and perfectly inelastic collisions. If the kinetic energy is not conserved in all inelastic type of collisions, what could have happened to it after collision? Yes, some of this kinetic energy is lost and transformed to some other forms such as heat, sound, and other energy types. Elastic and inelastic collisions are closely similar since the objects separate after the collision, except that the objects got deformed and kinetic energy is not conserved in inelastic collisions. How do we know that the kinetic energy is not conserved? We can use the law of conservation of energy concept represented by this equation to check if the kinetic energy is conserved. Since Ka is equal to mv squared over 2, then the equation will be m1 v1 squared over 2 plus m2 v2 squared over 2 equals m1 v1 prime squared over 2 plus m2 v2 prime squared over 2. If the calculated kinetic energy before and after collision based on this equation are not equal, then kinetic energy is not conserved, since some of the kinetic energy is lost after the collision. Then, the total kinetic energy before is greater than the total kinetic energy after the collision. If the objects separate after the collision, use this formula. m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, where m1 is the mass of the first object, v1 is the velocity of the first object before collision, v1 prime is the velocity of the first object after collision, m2 is the mass of the second object, v2 is the velocity of the second object before collision, v2 prime is the velocity of the second object after collision. If the objects combine after the collision, use this formula. m1 v1 plus m2 v2 is equal to m1 plus m2 times v, where m1 is the mass of the first object, v1 is the velocity of the first object before collision, m2 is the mass of the second object, and v2 is the velocity of the second object before collision, and v is the common velocity of the combined mass. Let us now apply these equations in these problems. A 0.2 kilogram ball moving to the right with a speed of 3 meters per second undergoes a head-on collision with a 0.4 kilogram ball moving at 2 meters per second speed. After collision, the second ball moves to the right with a speed of 1 meter per second. What is the speed of the first ball after collision? Is the collision elastic or inelastic? Now, to solve these problems, you can use GAFSA method so that you can make it easier and more systematic. So, let's start with the given. M1 is equal to 0.2 kilograms, V1 is 3 meters per second, M2 0.4 kilograms, V2 is negative 2 meters per second. Negative since we have a head-on collision here, so if the one is moving to the right, the other should be moving to the left. V2 prime is equal to 1 meter per second. We are asked to solve for V1 prime. Okay, so our formula here is M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, since the two objects separated after the collision. Deriving the formula to solve for V1 prime, we have M1 V1 plus M2 V2 minus M2 V2 prime over M1. Substituting the values, then do the math, and our V1 prime is equal to negative 3 meters per second or 3 meters per second to the left. Now, let's determine if the collision is elastic or inelastic. So, we need to determine if the kinetic energy is conserved here. Using the formula, M1 V1 squared over 2 plus M2 V2 squared over 2 equals M1 V1 prime squared over 2 plus m2 v2 prime squared over 2. Substituting the values, and then you do the math. The kinetic energy before the collision is not equal to the kinetic energy after the collision, which is 1.7 joules for the kinetic energy before, larger than the kinetic energy after the collision, which is only 1.1 joules. Therefore, the collision is inelastic since the kinetic energy is not conserved. Let's now proceed to sample problem number 2. A 0.25 kilogram arrow with a velocity of 15 meters per second to the east strikes and pierces the bullseye of a 7.0 kilogram target that is at rest but free to move. What is the final velocity of the combined mass? So the given quantities here are m1 is equal to 0.25 kilograms, v1 is equal to 15 meters per second, m2 is equal to 7 kilograms, v2 is equal to 0 since it is at rest. So we are asked to solve for the combined velocity after the collision. So since the objects combined after the collision, we will use the formula m1 v1 plus m2 v2 is equal to m1 plus m2 times v. To solve for v, we derive the equation v is equal to m1 v1 plus m2 v2 over m1 plus m2. Substitute the values, and then you do the math, and the answer for v is 0.52 meters per second to the east. We rounded the answer off to hundredths place. So it's very important also to indicate the direction since it is a vector quantity. Now let us have a summary of the types of collisions mentioned in the discussion. Elastic collision, the internal energy of the objects in the system does not change. So it is equal to 0. As shown here, example of elastic collisions are proton collisions, and the billiard balls are approximately elastic collision types. Next is inelastic collision. The internal energy of the objects in the system changes, so it is not equal to 0. Okay, example here. Examples of inelastic collisions are balls bouncing off the wall or on the floor. And the last one, the perfectly inelastic collision. Objects stick together and there is maximum kinetic energy dissipation, just like this. Example of perfectly inelastic collision is when you have two lumps of clay stick together. Okay, so there is a combined mass after.